Hello everybody. We're still talking about the mass transfer process between two phases, and we have already discussed the graphical representation of the mole balance equation and the equilibrium relation, and we saw how this can mean a lot for us when we represent these graphically, and we can see a lot of things visually using this graph. There is one other piece of information that's very important to us, which is the overall driving force. We mentioned earlier that we have an issue with dealing with the individual mass transfer coefficients because we don't know the interfacial concentrations. This is a parameter which are the P interface and C interface. These are parameters that we don't know how to measure, and it's not practically measurable parameter. So that's why we need to use other parameters that are more practical to use. And in this, for this case, we said we will use the overall mass transfer coefficient, and to make the equation correct, we have to use the overall driving force. And we said that this overall driving force is the difference between two pressures. So instead of having this PA minus CAL, we need to get another pressure that corresponds to CAL. And in order to make it like a correct or a value that is meaningful and will not violate the equation, we have to make sure that the pressure that we are going to use as the other pressure, which we will subtract from this to get the overall driving force, it should represent this concentration. And to represent this concentration, of course it's not going to be equal to it, but it will be in equilibrium to it. And that's why we will use what we call the P star, which is the pressure in the liquid phase, which is an imaginary pressure, but this pressure represents the concentration in terms of pressure, assuming that there is something like this. And the same here for the concentration. We said we will have another concentration here, which is gonna be C star, which is the concentration in the gas phase, which is in equilibrium with PA. When we say that they are in equilibrium with PA or with CAL, we mean that they lie on this line. So for the definition of for the liquid phase, if I want to do this for the liquid phase, then I should have a concentration that is in equilibrium with PA and lies on the equilibrium curve. So it's easy to find here. So what I'm gonna do is to extend this line here, which is the locus of P equals PA, and get the intersection of P equals PA with the equilibrium curve, and this concentration is CAL star. So this is the hypothetical imaginary concentration in the gas phase that is in equilibrium with PA. And now, since we mentioned earlier that this is the driving force in the liquid phase, we can now see the overall driving force. This is the liquid phase driving force, and this is the overall driving force from the bulk of the gas to the bulk of the liquid. The same for the gas phase, and of course we're going to use the overall mass transfer coefficient here, which is the uppercase K. For the gas phase, we have the same thing. The overall driving force is PA minus PA star. So the PA star is the pressure that represents the concentration in the liquid phase. Again, it's hypothetical imaginary value and it's gonna be in equilibrium with CL, so it's gonna be this point which gives this PA star, and in this case this is the overall driving force in the gas phase. So this is like a very nice thing. We can easily now see the overall driving forces. I'm sorry, I think what So now we can see the overall driving forces for the liquid phase, for the gas phase, and we can see how big is the driving force in the liquid phase compared to the driving force in or the overall driving force. So this is the driving force in the gas phase, this is, or the liquid phase, this is the overall driving force, and this is the driving force in the gas phase, and this is the overall driving force. So it gives us visually again a good idea of how the overall driving force looks like. Is it big? Is it small? Are we far from equilibrium? I'm sorry. Are we close to equilibrium? This is one very good thing that we can get from the graph. Now comes the question: how can we calculate this overall driving force? So now we have CA star, CAL, PA, and PA star. These all are parameters that we can calculate. If I know PA and I know the equilibrium relation, so I can easily tell what or calculate the value of C star. I can easily calculate the value of P star. It's as simple as we did it here on the graph. If I have the graph or I have a relation or an equation, just put the value of CL and get the P star, put the value of PA, get the C star. So I now can get the equilibrium or the overall driving force easily. But now comes the question, can I calculate the overall mass transfer coefficient? So I got this part done, but this is not known for me now, so I need to know how to calculate it. And to get this, we need to do some mathematical calculations, or derivations, but this is highly dependent, and this is very important. This is extremely important to know that this is valid. What we're gonna do here is valid for the case of linear equilibrium. This is based on the assumption of a system that obeys Henry's law. And in this case, we can say that P interface equals H multiplied by C interface. We can say that P star equals H multiplied by CL. We can say that PA equals HCA star. So this is the equilibrium relation that is valid for the 3 points: the interface, the bulk of the liquid, the bulk of the gas. This is where we are gonna apply this equation. And again, keep in mind that this is valid because it's a straight line, so it applies for the gas phase, applied for the liquid phase, applies for the interface. So if we go back to this curve that we have here, this is not gonna be valid in a case like this, because the slope here is different from the slope here, is different from the slope here. So and again, that's why I am emphasizing that this is valid for linear equilibrium, where the slope is constant all over the range of concentrations that we are using. Now, to get the relation, we need to start with the flux equation. So this is the flux for the individual mass transfer coefficient, or for the gas phase, for the liquid phase, for the overall. And we can do some rearrangement of the equation. So we can put the equation of 1 over kg equals P minus P divided by NA, 1 over KL the same, 1 over kg is the same. And we will do some mathematical manipulation to this. It's very simple thing. So I'm saying that P minus PA star equals P minus PA interface plus PA interface minus P star. So it's adding and subtracting the same parameter. It's minus PA interface plus PA interface. So I didn't do anything different. And for PA interface and PA star, they are already here. So I can substitute with these two terms in these two terms here. So it's gonna be HC interface minus HCAL, which are these two. And then we can take H as a common factor. Now, I'm almost done, but just look at these two terms. You will find that this is the same as this. You also find that this is the same as this. So we can now rewrite the equation in terms of 1 over kg and 1 over kl. So this is the overall mass transfer coefficient in terms of the individual mass transfer coefficients. So the equation is 1 over kg equals 1 over kg, the individual, plus h over kl. So this is now if you look at these, the terms on the right hand side, they're all known to me. If I am going to calculate the overall mass transfer coefficient, I always know the for this type of problems. Of course, you can calculate it using the formulas as we see in the next chapter, but this, let's say in this kind of problem, we know the individual mass transfer coefficients. We can calculate them, let's put it like this, and I know the equilibrium relation, so I know everything here, so I can now calculate the overall mass transfer coefficient, and based on this information I can calculate the flux. You can do the same procedure for the liquid phase mass transfer coefficient. You'll find that this is the equation. You can do this for Kx, for Ky. It's valid for all of them. So this is how you can calculate the overall mass transfer coefficient based on or in terms of the individual mass transfer coefficients. But again, I'm saying it again and again, this is valid for linear equilibrium relation. If the equilibrium relation is non-linear, this is not true. This is not right. This is something we will see in the next in the next video, inshallah. So this is like one nice thing also that we can see as a comparison between heat transfer and mass transfer. As we mentioned earlier, this is something that we're gonna mention a lot here. So this is what we have in heat transfer. If you have heat transfer between two phases, you will have HL and HG. Sometimes you call it H in and H out. So depending on the like the symbols that you use or the names that you give. Then this is the flux in the liquid phase, this is the flux in the gas phase, and this is the overall heat transfer coefficient, which is U. This is the overall driving force. And this is the relation between the overall driving force, the overall heat transfer coefficient and the individual heat transfer coefficients. If you compare this to what we have here, it's very similar. You'll see that we have two mass transfer coefficients. You will have mass transfer coefficient or the flux based on the liquid phase mass transfer coefficient, the flux based on the gas phase mass transfer coefficient. You will have different shapes or more than one shape of the mass transfer flux based on the overall mass transfer coefficient for the liquid phase or based on the gas phase, and you'll have this relation between the overall and the individual transfer coefficients. The main difference here will appear because of the equilibrium relation, because we don't have this as one point. This is the main issue. You have different units here while you have here the same unit all over the whole system. So this parameter appears here and the difference in the units because we have different phases with different units. So this is one thing that is nice to have as a good comparison between heat transfer and mass transfer. In the next video we will see how we can repeat the same procedure in case of having nonlinear equilibrium relation. So I'll see you then, inshallah. Goodbye.